So now we're going to talk about that pesky cavitation within our pumps and how to avoid it. If we remember from our lectures earlier, cavitation is a bad thing and it can cause damage to our pumps. Now as we take a look at things, how does cavitation happen? So cavitation happens when our system pressure drops below our vapor pressure. And if you go back to those initial lectures, what's going on is once we drop below the vapor pressure, we have the possibility that the liquid phase of our system is existing with the gaseous phase of our system, which means that if we're taking water, we can have water basically boiling at our normal pressure. So as I take a look at this picture here of this pump, it's when we bring the pressure into the eye of the pump on the suction side of the pump, we do get a pressure drop before it kicks back up. And what we're concerned with is to make sure that the system pressure here, and why is my pen not... We'll make sure that the system pressure here is above the vapor pressure. Because once the system dips right here below the vapor pressure, we start to have issues. So if you remember what happens when we have a fluid that is basically boiling inside of its own liquid, is we get these little bubbles start to appear. It's negative pressure because the pressure out here is going to be greater than what's going on inside. At some point we'll get to a maximum bubble size, and that's really going to have to do with the amount of surface tension in the bubble and the amount of pressure on the outside. And then what happens? Well, the bubbles start to compress and then they explode, they collapse. And then all that water, once the bubble collapses, starts rushing in. So if you look at what happens on the impeller blade, is you get all these little bubbles that are appearing here, and they start to collapse. And that's where the water hammering comes into effect, as that water is rushing in to fill that void that is now left, and it starts smacking on the impeller. And this is bad because it can really damage devices. And these are just all pictures of impellers that have been pitted by this cavitation process. Now, if you're on a ship or near a pump and you hear it start making a lot of noise, and I'm sure, especially where we're at, a lot of you, when you've been out on the ship, you've heard the propeller cavitate. And it makes a god-awful amount of noise, and this is what's going on, and it's a bad thing for our system. So the question is, how do we avoid that? Well, as we look at it, to characterize the potential for cavitation, we have to look at the difference from the total head on the suction side. So this is everything coming in to the pump. I don't really care about the outside, it's all about the suction side. So we're looking at the total head on the suction side and the liquid vapor pressure head. Now the liquid vapor pressure, we can look up, it's tabulated by fluid. And so the total suction side head is going to be the pressure on the suction side divided by gamma to give us a head rating. Plus we have to worry about the dynamic portion of that. So the velocity on the suction side over 2g. And so the vapor pressure head is just the vapor pressure divided by gamma. Now the one thing to note when we're dealing with vapor pressure, especially as you look it up, this is always going to be an absolute pressure. So you need to be careful when you're calculating things out that you're sure that the suction side pressure is going to be also an absolute pressure. So the difference between these two, so pressure on the suction side over gamma, V squared on the suction side 2G minus PV, we give this a term, we call this NPSH. That stands for net positive suction head. And this is that NPSH line that you've seen on some of the pump curves up until now. So there are two types of NPSH. The first is what we call NPSH-R, which stands for required. Now this is how much net positive suction head that you need, the specific pump needs to avoid cavitation. Now typically this will be given to you on a pump curve, as we've seen previously, and this is what the pump needs. If the pump does not have this much net positive suction head, the pump is in danger of cavitation. And then we have Npsh available. Now this is how much net positive suction head is in the system that's available to the pump. So you can either find this experimentally, you can set up your piping system and calculate this out, or you can just solve it from the equation. So if we take a look at it, what we need to remember is for a system to properly operate, you have to have more available head than what is required by the system. And that's an issue that you're going to have to calculate out. Is there enough net positive suction head available to run my system? Now the next question is, well, how do I calculate this out if we're not going to do an experiment? So let's look at our energy equation. So that's our N equals all of this stuff going out. Now this is where we're going to get into drawing a second control volume for our system. Because what I'm going to end up doing is if I draw a control volume that ends right at the inlet to my pump, instead of being on the out, what that's going to give me is it'll give me the suction side of the pump. And so then I can go calculate what's going on into the suction side of the pump. Now the problem we have is that gives us this part here for our net positive suction head, but it doesn't give us our vapor pressure head. So the next thing I want you to look at is, do you all agree with me that what I just did the equation, I added one, subtracted one, I've not changed the equation in any way whatsoever. That is the exact same equation. Adding and subtracting one doesn't change anything. So hopefully you all agreed with me there. Now, you should agree then that I can add the vapor pressure head and subtract the vapor pressure head from my equation. Because once again, I haven't changed anything because I've added and subtracted it. But now what I can do is I can take these terms here, put them together, and call that my Npsh available. Solve the rest of the system. Now this gives you the net positive suction head available right to the incoming part of the pump. Now in a bigger piping system, what you may have to do is you may have to draw a couple different control volumes. So if we go into one pump there, and then another pump there, and then there's some exit, well, we may have a control volume here for the first pump for Npsh. Might draw a second one here to calculate the Npsh in the second pump, and then we might have a third control volume over the whole thing so we can do our normal energy equation and calculate out what's going on with the pump. So the important thing to remember here, though, is we're going to do this for every single pump in the system. Now, typically, in this class, we'll only be calculating out one, but it just means that we're spooling up a second control volume. So you'll see on a couple of these examples, we have a big piping system. We're going to have two control volumes because we need one specifically to find the net positive suction head available. And as long as we have more available in our system than what's required by the pump, we should be fine without any problems with cavitation.